All right, we have some grounding now to go back and clear some of the derivatives that we've had in our list that we kind of waved our hands about. So what I'm going to start with right now is we're going to look at um, the natural log of x as a function. And we know that natural log of x is the inverse of e to the x. So we're going to use this relationship to explore the natural log of x. So what we're going to say is our original function is e to the x, which has a derivative of itself. And we're going to ask, what is the derivative of the inverse of this, which in our case is natural log of x, at any point x. So we are asking, what is the derivative of the natural log of x? Well, we're going to use our inverse relationship then. We're going to say that this is going to be equal to 1 over f prime of x evaluated, and we're going to evaluate it at the inverse. So 1 over e to the x evaluated at x equals ln x. Because that's the point that we're looking to work at. And this relationship tells us then that we get 1 over x. Because e to the x ln x, these cancel out and leaves us with x. And so we now have that the derivative of the natural log of x is equal to 1 over x. And inverses, since they were very useful things for us, we'll fill in some of our derivative tables. Let's look at an example of this. Let's look at the derivative of the natural log of the absolute value of x. And this has an interesting thing because the natural log in its normal state only exists for positive values. So if I take the absolute value, we get this kind of conical relationship coming here, right? And there's a symmetry here, so we should be seeing slopes where, or when we look at these slopes, they are negatives of each other, right? They're running in the opposite directions, but they're mirrored across the y-axis. And so let's look at this derivative. And we're going to have to use the chain rule here now. So what we're going to say is the absolute value of x will be u. And that means then that we'll look at this in the form of d dx of ln of x is equal to, using the chain rule, d du ln of u du dx, right? The derivative with respect to u times x. So du dx, well, du dx ends up being, for the derivative of the absolute value of x, it's going to be x over the absolute value of x. Now, how did we get this, huh? How did we get x over absolute value of x? Well, let's look at the chain rule happening here. And we'll look at the chain rule. How do I want to look at the chain rule here? Yeah. I think we did this when we did this. We said we're going to make this. I think I did this on the board in class. We used this relationship. And then we said du dx then is going to be x squared to the 1/2 power. So we brought it as 1. Right? We used this chain rule. And we said this relationship holds true because this is the same as the absolute value of x. It's kind of hard. I remember showing this relationship often in classes because how the absolute value can be the same as x squared square rooted. So we could look at this as some w function. So we'll have 1/2 of the w function. Let me write this all out. I know we did it on the board, but let me just write it all out. So I'm going to say that this is going to be equivalent to x squared square rooted. I'm then going to say that u is equal to some form of it where the overall form is, I have the square root of w, and w is equal to x squared. So u is equal to w. W is equal to squared. So du dx is dw dx. Or, sorry, d dx. Square root of w, dw dx. And here at least we get a nice w is 2x. And so we put all of this back together, and we get that this becomes 1 over 2w times 2x, and we put w back in, and we get to the 1/2 power. So we get the 2's cancel. We get x upstairs, and we have the square root of x squared underneath it, which is the same as x over absolute value of x. So this loops all around on itself. And for our notation point, this is not a bad way of thinking right now. That du dx is x times the square root of x. So if I continue on with my derivation after my long little warble here of the natural log of x, then using the chain rule here, the derivative would be 1 over u times x over root x. And 1 over u, well, what was u again? It was the absolute value of x. And the absolute value of x is x over x squared. I'm going back to this definition here, because if I multiply 2 of these together, that's the same as x squared, or 1 over x again. And so we find that the natural log of the absolute value of x is 1 over x. The only thing that happens here is it can't exist at 0. We can't, nothing, right? It's asymptotic to 0. So just the nature of the function, x can't be 0. Well, it also can't be 0 because of the division there. That's what's driving these asymptotes. And this becomes really important because natural logs and e exponentials are, because e is its own derivative, it becomes a very useful function for solving differentials. And we have to do these things backwards. And when we solve some of these things backwards, it will split us into positive results and negative results. And we might not know what's happening at x equals 0 because of the nature of this absolute value function. And so we just have to keep in mind that sometimes when we see 1 over x, when you're in Calc 2, Calc 3, ODE, and going backwards, the answer isn't ln x, it's ln natural, ln absolute value of x. And we should see that we're getting an equivalence of the derivatives here. The rule I remember is the derivative of this is equal to 1 over x. And then later on, when I'm in integral calculus and looking at the antiderivative, I look at the antiderivative as being with the absolute value. And the nature of the problem will tell me if I'm looking for positive versions of it or negative versions of x. The domain will tell me what's happening. But it's kind of nice that this rule that we use now kind of shows us where these things are going, and we can start building some things for inverses. So we have now that our derivative of the natural log of x is equal to 1 over x. And I think the next example I'm going to look at is I'm going to look at any power and any logarithm in the next video. And then we'll look at using logarithms to help us differentiate. And that'll close up today's lecture.